Today we're going to have a look at flag-style derivations. So flag-style derivations are a nice way of proving whether given propositions are tautologies. It's basically an alternative to writing out a whole proof in words. You could just use flags where the flags have meanings, and we will see what they mean right now. It is generally more structured, and you use flag-style derivations right in the beginning of learning logic and set theory, and this is because it helps you see how to prove different types of propositions. For example, if you have a implication, so P implies Q, how do you prove this? Or if you have an OR, like P or Q, so what steps you take to prove a proposition like this, and more complex ones, which we will see in this video. So in this video, we're not going to go over all the rules, which you can find in a table at the back of the Logical Reasoning, a first course book by Rob Nederpelt and Fairouz Kamareddine. But we're going to see how we apply them. So let me just erase this. And let's write down what question we're going to prove today. So the proposition we have today is, I'm going to write it on the right so we can do our working out on the left. So we're given the proposition P or brackets Q and R, so all of them brackets, implies not P implies Q. This is the style of questions we use flag-style derivations for. They're usually easier to solve and more organized using flag-style rather than writing it all out in words, and it's also usually faster. So the main idea behind flag-style derivations is you take the proposition they give you and you use backward reasoning to simplify the goal as much as possible. And you'll see what we mean by that in a second. But so you simplify the goal as much as possible using backward reasoning. And when you can't simplify the goal anymore, then you start using forward reasoning mode to finish the proof or the derivation. So I'm just going to copy the proposition we're giving. So it's P or Q and R. And this implies not P implies Q. So this is what we call our goal. So this is what we're trying to prove. And like we said, we're going to use backward reasoning to simplify this goal as much as possible. And the way we do that is, well, we look for the main connective. Well, if you can see, the main connective here in this question right now is an implication. And according to the rules you're giving, the way you prove an implication is to assume the left-hand side and try to derive the right-hand side of the implication. So if I just write it down on the right real quick. So for example, if you have P implies Q and you want to prove this, well then what you're going to do is assume P. You assume P and you try to derive Q. And in flag-style derivations, we put our assumptions in the flags. That's where the name comes from. So we're going to write our hint first of all. So our hint is just going to be implication introduction on, well, we don't know what lines, on lines blank and blank. And then we're going to draw our flag, and the flag is until here, and we're going to draw a flag right here, so right there. And we said we're assuming the left hand side, and the left hand side is all of this in blue, so we can see it's all of this. So let's just put it there. So this is our assumption: P or Q and R. And what we also do is write assume before every flag, and this is just standard. So here we just say assume. And even though we know anything in the flag is an assumption, we just write assume to make it more clear. So we assume the left hand side, and we have to derive the right hand side. So on the right hand side is our new goal. So if I highlight it, this is our new goal. So we write our new goal on top of here. So not P implies Q. And you can see that we're using backward reasoning, and we went from this big implication down here, right here. We went from this implication, which is a lot harder to prove, to this simpler one. Now we said we use backward reasoning as much as possible. So we see that the main connective here again is an implication. So we do the same thing. We assume the left hand side and we try to derive the right hand side. So we say implication intro on lines and we draw a flag again, and we write assume, and our flag goes right here. And what goes in our flag is the left hand side, which was not P. And let me make this flag a bit smaller because it's taking up way too much space and we don't need it to be that big. Okay, and our new goal is just to prove Q. So now you see we just have Q as our goal, and we can't simplify that anymore, or at least I don't think so. So this is where we stop using backward reasoning mode and we start using forward reasoning. So we have some assumptions. We have two assumptions. We have two flags, so two assumptions. And what we can do is use these assumptions to derive Q. And one thing that's very important to not forget is number your lines. So this is line number 1. This is 2. And these ones we don't know because we don't know how many steps we're going to need here. So we don't name these steps yet and these lines yet. So this is line number 1, line number 2. So let's look at the assumptions we have so far. We have in our first assumption an OR as a main connective, and on the left hand side of the OR we have a P, the proposition P. And then notice that in the second assumption, which is the second flag, we have a not P. So we've assumed P and not P. And if you look at the rules for OR elem, you know that if we have an OR statement and then you also have the negation of one of the propositions, then you can use OR elem. So let me just write down what I mean. If we have a derivation and somewhere in the lines of our derivation we have the statement P or Q, so we know this is true. So what does this tell us? Well, this tells us that either P is true, Q is true, or they're both true. So we know one of them has to be true, at least. And somewhere else, so we don't know what line it is, but somewhere else we know that the proposition not P is true, right? So we know that not P is true. Well, what does that tell us? Well, that instantly tells us that Q has to be true, because the OR tells us that either P is true or Q is true or they're both true. And we know that not P is true, so that means, well, P can't be true because we know not P is true. So the only option we have left is Q is true for this to be true, because we know this is true. So let's apply the same logic here. We know that in the first assumption that either P has to be true, Q and R has to be true, or both of them have to be true. And we also know that not P is true. Well, that means that P is not true because we know not P is true. So we can use OR elem, and we have to write the lines on which we're doing the elimination. So it's on line 1 and line 2. And so what are we left with? Well, we're left with Q and R. So we know Q and R is true. And this is line 3. And now we're almost there. We wanted to prove Q. What we have now is Q and R. We know that Q and R is true. Well, what do the rules tell us about conjunction? So if we know that P and Q are true, or for example, in this instance, let's just stay with the same variables. If we know that Q and R is true, then what does that tell us about Q and R? Well, that tells us that Q is true and R is also true. Because for a conjunction to be true, then both of the conjuncts have to be true. So if we know that the conjunction is true, then both of its conjuncts is true. So here we know that Q is true and R is true. So what we're going to do is just simply use and illum, and that's on line 3. We don't use any other lines, so we just use line 3. And we don't write anything else, because when we do and illum, well, that means that we know that Q is true. So we can just draw an arrow for the empty space, but we've finished our derivation. And now we said always remember to write the lines, so this will be line 4, because there's nothing else there in between line 3 and line 4. This will then be line 5, and this will be line 6. And we also have to fill in the line numbers here, 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 and here. So we did a implication intro on line 2 and 4, and also here it was 1 and 5. And if you're wondering what these lines are, well, these are just lines to help the reader know what you're doing. So here when you write or illum on line 1 and 2, they know you're eliminating the or. Instead of making them guess well, right now it's clear, but like in harder propositional statements, it might be not clear between which two rules you are using. So it always helps to have a line saying what you did. And like I said, we're done because we simplified our goal as much as possible. We wanted to prove Q, and we derived Q. So that means that this proposition here is a tautology. And when we manage to use all the base rules that we are provided with correctly, if we manage to apply them correctly, then what we should get is we should find out whether the proposition we were trying to prove is a tautology or not. So here in this case, we see that we managed to finish the proof without any problems. So that means that the proposition here that we started with, it is a tautology. And a tautology means that it's always correct. Doesn't matter what values you give P, Q, and R, that this proposition would always be true. Hope this video helped clarify how to use flag style derivation in your proofs, and thank you for watching.